Hi everyone, I'm coming to you today from my living room, as we do nowadays, to share information on molecular spectroscopic data, particularly for astronomy. Yes, that is a Mauder's map in the background. Um, I like Harry Potter. So, what are we here for? We're here to talk about astrochemistry. So I'm all about molecules. I'm actually trained largely as a chemist, though I have worked in a physics department. And it's all about molecules in planets, stars, the interstellar medium, and lately exoplanets have been the big thing. So spectral data is needed in order to find molecules anywhere. And really, in order to find that spectral data, we want to combine the best theory, which is normally quantum chemistry. You solve the Schrodinger equation using as big a supercomputer as you can get, as accurately as you can get it. And then you actually need to combine that with theory to get the best results. So just as a broad overview, experiment over here gives you the best frequencies, but only for the spectral range measured, only for a small number of lines, whereas theory gives you a better answer for intensities and also gives you a much more comprehensive picture. And if you combine these two sensibly, you can get really high accuracy, really accurate accuracy in frequencies, accuracy in intensities, and that coverage that you're really wanting for many applications. Okay, so most of you probably know about the recent discovery, life on Venus, maybe. So traces of phosphine may be a sign of biological activity. And I know that the detection is disputed at the moment through processing concerns and things like that. But from a chemist point of view, from a molecule point of view, I'm looking at this problem as look, this is a test situation. Maybe there's life on Venus, maybe there's not. But any other exoplanets, we're going to go through the same scientific process. And the advantage of Venus over any of these exoplanets is we can send a probe there and see if we're right. So when I heard there was phosphine on Venus, I said, well, what about all the other phosphorus containing molecules that might be on Venus, that might be precursors, that might be products of those molecules, so the reactions that are taking place. And I found that actually there's not a lot of spectral data on that. And I'll go through it a bit today, the process of what we did on this. So the first approach, when you're looking at phosphine on Venus, when you're looking at any of these sort of systems, you can target specific molecules. You can say, I know this molecule is useful. I'm going to produce spectral data on this molecule, and I'm going to spend a lot of time to get it as accurate as possible. And in my postdoc in the XML group, the group is centered at University College London, but now the XML brand has really become it's a database, and it's got spectral data that's produced at UCL. It's got spectral data that is produced all across the world. And the XML creation approach considers individual molecules. So I particularly studied TiO and BO here. And it aims to get a list of essentially every energy level and every transition intensity that it can get its hands on. You combine experiment, theory, it's molecule specific, and it's time consuming. So it took me years as a postdoc who knows what she's doing with this sort of electronic structure theory experimental data. It took years to create these line lists. There are new approaches I want to highlight that are suitable for very high resolution studies. So initially, a lot of line list data was produced assuming that the astronomical resolution would be very low. So in exoplanets, space-based observatories, the resolution is very low. But if you do ground-based observatories, your resolution is very high, but your noise is very high. So what you actually do is there's this cross-correlation technique where you say, well, here's my expected signal and here's my actual signal. And the actual signal is hidden among this huge noise. But if you cross-correlate those signals over a large enough spectral range, then you can actually detect molecules. So a lot of the new detections, for example, of TiO, were done using cross-correlation, using ground-based instruments. But in order to do this, they need very, very high resolution. And I'm not going to talk a lot about this at the moment, but I really just want to encourage you to contact me, contact any of the XML team if you're interested in specific new molecules. So this is the list of molecules that XML has looked at and got line list data for. It's expanding all the time, but how we add molecules to this list is an astronomer or an experimentalist comes to us and tells us, I want to study this molecule and I can't find any data on it. We add it to the list and see how hard it is. The other reason you might want to contact me is to understand the errors. So obviously there's lots of things that go on when you're constructing these line lists, and I'm very familiar with all the different things that go on and the approximations that are taking place here. And you might not realize, for example, that the visible region is much, much harder to calculate accurately than the infrared region, because the electronic structure is much more complicated than vibrational structure. And so if you want to know sort of molecule specific, spectral region specific, is the data available good for this, I can sort of talk you through that. Or you can obviously contact the original line list creators is also a good option. Okay, so sometimes the existing data isn't good enough. So this was the case in 2015 when, where have I got? Yeah, okay. So I'll talk you through this figure. X-axis is wavelength, y-axis is normalized flux. The black line is an M dwarf, and we know that M dwarf definitely has titanium oxide because that's what characterizes what an M dwarf is. Now this orange and green and blue are different models of titanium oxide. And what they wanted to do is they wanted to do that cross correlation, that matching. But if you look at these different things, then the dips in the experimental spectra half the time are correlated with peaks in the theoretical predicted spectra. I mean, sometimes they're correlated properly, like this feature here seems to be represented properly, but other ones are completely off. And it's just trying to find a signal in this is useless. And for any chemists in the audience, this is sub-wave number accuracy. This is about 1,000 times more accurate than chemists would call chemical accuracy. So a lot of our modern methods don't do this very well. Well, it doesn't accomplish it at all if you're just using theory. If you add some experiment to it to refine stuff, you can get there. So that's what I did in this particular paper. So my data is this green one, Toto. And you can see this green data matches much more closely to this black data. And that green and that black can actually be used to find titanium oxide in exoplanets. So I produced a line list with astronomers, with chemical physicists. We worked together and produced a line list. It's suitable for high resolution cross correlation. Really the key is that you've got the experimental data, you take everything you can out of the experimental data, you get your theoretical models and you fit them. Yeah, so that's there. This titanium oxide is really important for M dwarfs. It's also an extremely hot topic if you're studying hot Jupiters. So it's anticipated that titanium oxide might cause a temperature inversion. So sort of like the stratosphere, the temperature decreases, then it increases. That's being studied, very hot topic in hot Jupiter research. That's a bit ironic. But yeah, this sort of line list enables those studies to be on much firmer footing than they were previously. Okay, so when I started to think about the phosphine on Venus problem and we thought, how are we going to do this? What I actually did was get basically everyone I knew that had anything to do with this problem. So I wanted some spectroscopy data people, I wanted some microwave astronomers, I wanted some experimental spectroscopists, I wanted origin of life and geology experts, kinetics people, and of course some enthusiastic undergrads who could help us process the data and learn heaps in the process, hopefully. And the idea is when we actually got all these people together and I said, what phosphorus molecules do you expect to find in Venus? What phosphorus containing molecules are in Earth's atmosphere? What's happening there? And then I actually looked at all the line lists and went, well, what data is out there for phosphorus? And it turns out not very much. So I'll just say here, my naive challenge to the team was I want to find I want a list of every phosphorus containing molecule that's of potential importance in Venus. And it turns out little research has been done on phosphorus molecules. So this is not our final list, but this is a list of the phosphorus containing molecules that we found that were somewhat relevant. There were line lists, I think, for phosphine full stop. And then I think pH2 had a line list as well. So really there was no data on this anywhere. And it turned out the reason for that, the dominant reason for the lack of data is actually in the Earth's atmosphere, the phosphorus cycle, and I didn't realize this because I'm not an origins of life, I haven't done biology at all. Phosphorus actually goes from the rocks. It's really hard to get it from the rocks to the water. That takes a bit of explaining. And there's actually all these papers on the phosphorus problem. But once you get it into the water and the forms of phosphates, it goes from the water, it goes into biology, the biology degrades, it goes back into the water, and it goes round and round and round. But the atmosphere actually doesn't really take part in any of it. So the atmospheric phosphorus molecules are really, really rare. Phosphine's the most common, but it's still like parts per trillion. I've probably got that order of magnitude, but very, very low abundance. So really there was only data for a couple of diatomics. Diatomics are, well, they're easier to study in many cases. Well, they're, especially the phosphorus containing ones, they don't have a lot of the complications that the metals do. So titanium oxide is particularly complicated because the titanium is a metal and metals are colored, and that means they've got a lot of complexity electronically. Whereas phosphorus oxide, phosphorus nitrogen, it's really only one electronic state that's important. Anyway, that's details. The important thing is that not many molecules had good data. So what are we going to do? If you've got, remember, you've got no data, you have no chance of finding the molecule. If you don't have any data, you can't find it. So the alternate approach was to use a reaction agnostic approach. So rather than trying to find specific molecules, we look instead at a large number of molecules, produce approximate spectral data for all of it, and see what we've got. So these are preliminary results. They're under peer review at the moment. Yeah. So I do want to, so the idea here is we do a large number of molecules, we do it approximately, we do it much quicker. So we do it on bulk rather than individual molecules. And really the pioneer for this process was Dr. Phosphine, i.e. Dr. Clara Sousa Silva, who is now at Harvard. And the idea here is, she said, I just want approximate data for as many molecules as I can figure out. And her approach was something called Rascal, which basically looked at molecules as functional groups. And it said this functional group will absorb at this frequency, this functional group will absorb at that frequency. And if we take a molecule and break it into its functional groups, we can calculate its approximate spectra. Now, if I was to present this to organic chemists, they're like, well, of course, that's what we do all the time. That's actually what we teach our, first year, second year undergrads. We teach them, CH absorbs at 3000 wave numbers, and that's the big peak you've got here, and then all these different things. But actually automating this, making it systematic, programmable, was something that Clara did for the first time, which was really powerful. And so she produced spectra, approximate spectra for about 16,000 molecules really, really quickly. So you can look at this paper for some more details. This is just a count. So this is saying there's lots of, this has got 16,000 molecules approximately. And it says, what are all the spectral features in those molecules? And you've got lots of molecules that have this bond, a few with pH, and not many with other things. And I mean, this immediately, if we start to focus on the phosphorus containing functional groups, there's not much activity, there's not many competing molecules in the 2000, 2500 region, this region where the pH stretch is really dominant. It turns out actually at a stretch you can't see, CO2 has a stretch around here, just above the pH 3 stretch, but they can detect that reasonably accurately and sort of filter it out, hopefully. Okay, so what I did when I saw Clara's approach, I said, well, that's fantastic to do at organic chemistry, but I'm a quantum chemist. I want to put it in a computer. I want to solve my favorite equation, Schrodinger's equation, and see what happens. So we put it in a supercomputer, we solved the Schrodinger equation, we figured out wave functions, vibrational frequencies, all those sort of things. And the idea is really we just let the computer do the work for us. So we use the phosphine detection in Venus as sort of motivation to trial our full approach for predicting the infrared and microwave spectra of P molecules. So remember, this data was created very quickly, like as in 2 months. And the idea was I'd spent a lot of time in the past, and I'd seen a lot of people in the past try and get every nitty gritty detail finalized. And that's great when you're doing the details. But I also have to admit, I spent a lot of time trying to calculate things really accurately, got to the end of it and said, if I just put 0 for this value, there would be no difference to anyone. So this time with my PhD student, I said, I want to go all the way through. I want some answers, and then we can figure out which factors are important and spend our time refining the important factors, not the ones that are going to be relevant. And we also, this was the first time we'd really looked at this approach. Is this approach going to be much better than the Rascal approach? What information can we get out of it? And I would say at the moment, we've done a preliminary assessment of the information, sort of done a broad brush approach, but there's so much more detail in there to get into. Okay, so the first thing we did was 959 P molecules with scaled harmonic frequencies with this quantum chemistry model. Basically, this is what a black box method of quantum chemistry. So it's normally pretty good. It will fail at times and we don't know when, but we just sort of deal with it. This is one, I want to highlight him as the PhD student who's really leading a lot of this work. He is leading a lot of this work, obviously. He's got some support people, which is awesome. And he generated all this data really quickly, analyzed it, really great person. He's only in his first year, but when he finishes, definitely look out for him. So this plot here is showing the difference between Rascal and the scaled harmonics, which is our quantum chemistry. And the biggest difference, so CompChem, the biggest difference is that CompChem has molecular specificity for the position of functional group peaks. So Rascal just had like one big CH group here, and quantum chem just sort of spreads that out and says, well, actually the molecular environment affects the frequency. And we know that that happens in reality. So, I mean, this indicates to me that quantum chemistry is going to be more molecule defining. It's definitely more expensive though. The other thing that's really useful is that CompChem predicts this fingerprint region, this low frequency. So it turns out take a big molecule and you've got individual bonds. When they move, when they vibrate, they're going to vibrate at high frequencies. But when the whole molecule moves, then they're going to vibrate at very low frequencies. But that whole molecule movement, you can't predict using a functional group approach. It just is impossible. So there's literally no data. I would caution that the quantum chemistry, it gives you some idea down here, but this region is hard to predict. I wouldn't like to trust it too much, but it gives you an idea and it gives you a starting point and, you know, an indication, well, actually there's a lot of frequencies in this region that might be useful astronomically. So this is more the far IR region, which is often ignored. So this is the harmonic data up the top, and this is a more accurate data called unharmonic VPT2, just a better method basically. And the idea here is that we've got the harmonic frequencies, which are the strongest ones, but we've also got a whole bunch of weaker ones, which are the overtones and combination bands, and we can just sort of start to analyze those. Basically here we can figure out all the absorptions of the molecule using anharmonic, whereas harmonic only gives us the strongest. So it depends what you're after. There's numerous bands at various regions, but they're really low intensity. So the intensity of these harmonics or the anharmonic, the fundamentals, is a lot higher than the overtones. So this is probably the spectra that the figure you've been waiting for. Red is experiment here. Black is the anharmonic data that we predict, and Rascal is in blue. So we're doing better. I think, than Rascal in general. Some spectral lines are missing from both predictions, which to me indicates maybe there's a problem with the experiment. CompChem does better with the intensities, and that's expected because Rascal is basically saying this is 1 or 0, or 1, 2, or 3, I think it uses. Yeah. We've got some missing things. I know I'm running out of time. Some conformers, isotopes, rotational broadening, and we plan to investigate better methods to make it more accurate. Quantifying the difference in the spectroscopy of different molecules is really important and actually hasn't been done as much as you think it should have been. And identifying, this is probably the one that's most relevant for astronomers. When you think you've found one molecule, have you actually found something else? We want to group molecules into clusters so that we go, these molecules will be indistinguishable at such and such resolution with your telescope. So if you want to distinguish between this molecule and this molecule, you need something better than, say, GWST. Of course, you can then make arguments, well, this one's likely to be much stronger based on kinetics. This one's likely to be much more abundant rather based on kinetics. But that indistinguishability and figuring out possible ambiguities is really a key advantage of this method. We've got some progress on the microwave data. These are rotational constants that can be converted to line lists through some maths, basically. Dipole moments tell you how strong the transition is. So we've actually got some plans. We probably can't trust the frequencies, but the intensities we probably can trust. So we can say, okay, this molecule is going to be a strong absorber. This one might be really abundant, but you're not going to see it. And I mean, in the infrared, O2, N2 don't absorb infrared light. That's why they're not greenhouse gases, but it means that the dipole moment is important in that process. So in conclusion, high resolution data is important for many applications, essential, especially that cross correlation, the titanium oxide TOTO line list I talked about before. It's challenging, but very rewarding. As a quantum chemist, I can say I love the astronomers for giving me all these awesome molecules to look at, develop new methods on. Thank you. It's useful to astronomers immediately. Experiment and theory are both needed, but there's a complementary approach that I think's been less explored. And that's really doing high throughput predictions, hundreds, even thousands of molecules. They're possible, it's useful, and there's new approaches that we're testing at the moment. And basically, I love spectroscopy. Thank you. Look forward to hearing your questions.